5 for Questions talk by Facundo Rost, who is a PhD student at the University of Amsterdam. And he will speak about a new twist on spinning anti-de Sitter and de Sitter correlators.
Okay, thanks for the introduction. Yes, I will talk on this paper based on this recent work published together with Daniel Baumann, Gregorio Mathis, and Guillermo Pimentel. So to start, let me state an important challenge in the cosmological bootstrap community, which is that correlators of massless and spinning particles in the boundary of de Sitter and anti-de Sitter are complicated objects. In contrast, when we look at flat space amplitudes, they are very simple when we write them in terms of convenient variables. For example, there is the classic example of the so-called Parquet-Taylor amplitude, which is an endpoint amplitude of n-gluons in Yang-Mills theory, where exactly two of them have helicity minus. And this amplitude can be written in terms of this very simple formula, in terms of these so-called spin or helicity variables. While if we write this same amplitude in terms of the more usual momentum and polarization vector variables, we will obtain an expression of this scattering amplitude that is way more complicated. It will involve like adding up, for example, for n equals to 6, you will have to add up like 200 terms, which correspond to the 200 Feynman diagrams that you have to add up to obtain this amplitude. But the nice feature of these variables is that since they make all the kinematic constraints of this amplitude manifest, then the resulting expression of this observable in terms of these variables is very simple. We therefore suspect that the reason why our correlators, our massless and spinning correlators in the boundary of four-dimensional anti-de Sitter or de Sitter, the reason why they are complicated is because we are probably using inconvenient variables for these observables. Okay, so what variables are convenient? Well, the right variables must make manifest all the kinematic constraints because in this way they will be able to expose a hidden simplicity of the observable that we care about. Firstly, they must trivialize the space-time symmetries, which for the case of de Sitter or anti-de Sitter 4, they get translated into a conformal symmetry in the three-dimensional boundary. And secondly, they must make manifest the fact that we are dealing with massless particles, which translates into a conservation condition in the currents in the boundary. So the correlators of these boundary correlators of conserved currents that we are going to study, they must satisfy this conservation condition. Hence, our goal in this work is to find new variables that expose the hidden simplicity of these boundary correlators by making manifest all their kinematic constraints. And well, the upshot is basically that we are able to do this, to make manifest all these constraints when we write down our correlators in twistor space. And here you can see what happens when we write down our correlators in different spaces. So these boundary correlators of operators inserted at the boundary that have some interaction in the bulk. Usually in cosmology, we write them in the so-called Fourier space, where current conservation is easy to implement, but it is very hard to make conformal symmetry manifest because special conformal transformations are very complicated in Fourier space. In CFT, people like to work in this so-called embedding space, which is a higher dimensional Minkowski space where the boundary, this three-dimensional boundary is embedded. In this embedding space, conformal symmetry is trivial, but current conservation becomes now hard to implement. What I will show you is that if we write down our correlators in twistor space, we will be able to make manifest both of these constraints. And this is the reason why we will obtain much simpler expressions for our correlators in this language compared to this other language. Good. So let me explain in a bit more detail the embedding space. Right. So in this embedding space, we can map points in this three-dimensional boundary, R3, to light rays in the null cone of Minkowski 5. That is points in Minkowski 5 that satisfy p squared equal to 0. And since we also mod out the scale of this point, that's why we're talking about light rays. The reason why we like to work in this embedding space is because conformal transformations in this three-dimensional boundary are translated into Lorentz transformations in this five-dimensional Minkowski space. And hence, it is much easier to trivialize the conformal symmetry in Minkowski in this embedding space, because if we just say that, for example, our correlator depends only on products between vectors in embedding space, then this object is trivially invariant under any conformal transformations. Hence, we can just trivialize conformal transformations by working in embedding space. Then the next step that we're going to do is to trade this vector in a main space, this five-dimensional vector, by two spinors with two components each. These spinors have so these two we're going to trade with two spinors that have four components each. And the way that these two spinors, lambda1 and lambda2, are defined are in terms of this 4x4 matrix P slash that we obtain by contracting this five-dimensional vector with the gamma matrix of Minkowski 5, and by writing down this 4x4 matrix as a tensor product of spinors. This is the way in which these lambda spinors are defined. Hence, a generic operator will be like some function of this position PM that we translate into a function of these two spinors, lambda1 and lambda2. Great. But now we would like to impose conservation on this on our current. And it turns out that similarly to what happens for two DCFTs, where conservation is trivialized by the fact that, for example, a conserved current in two DCFT is like split into a holomorphic and anti-holomorphic piece, like J and J bar. For the case of three-dimensional CFTs, we can trivialize conservation by considering a holomorphic function of these two spinors, lambda1 and lambda2, in the sense that is holomorphic in the sense that it only depends on these two spinors, lambda1 and lambda2, through one specific linear combination. Hence, we can trivialize conservation through holomorphicity. And this spinor set that we obtain by considering this linear combination, we can interpret this object as a twister. Because in this map from these positions in embedding space to this space of spinors, we can interpret that we are mapping lines in points in embedding space to lines in this spinor space, and vice versa, points in this space of spinors to lines in embedding space. That's why we interpret this object, this spinor set, as a twister. Great. So a current in embedding space. Okay, so we want to trivialize current conservation for a certain current in embedding space. And we were saying that we can do this by considering a function that is holomorphic in the sense that it only depends on the spinors through a certain linear combination. But our current in embedding space shouldn't depend on these arbitrary coefficients of this specific linear combination. That's why, in order to obtain our object in embedding space, we need to integrate over these arbitrary parameters. So the procedure to go from this holomorphic function to the defining twister space to the current defining embedding space is by integrating over these arbitrary parameters. And in order to match the index structure of this current of spin S, we need to add a bunch of factors of pi that has, in order to have the same index structure in both sides of the equality. Great. So since this integral is holomorphic at the level of the integrand, then this embedding space current automatically satisfies the conservation condition. And also, this integral must be projective, because since we don't really care about the scale of the spinors, of the lambda spinors, we also don't care about the scale of the pi's. That's why this integral must be projective, and it will only make sense if the integrand scales in this way with respect to its argument. because in this way there will be no dependence on the scale of these pi variables. Great. So this scaling of the integrand implies that the scaling dimension of our current is going to be precisely equal to the spin plus 1, which is the value of the scaling dimension that saturates the unitarity bound in a three-dimensional CFT, and is the value that corresponds to a conserved current of spin S. Indeed, if we were going to make conservation manifest, it is natural that the scaling dimension was going to be forced to take precisely this value. Right. So now we can take this current in a main space, and we can write it in an index-free form by contracting it with a bunch of auxiliary spinors. And then the previous integral representation would look like this. And then we can perform a change of variables from these pi variables to set, to the twister. And this will allow us to rewrite our integral now as an integral over set instead of an integral over these pi coefficients. Where here we define this spinor epsilon in such a way that this product epsilon dot set is equal to this other product between zeta and pi. So this epsilon is just a spinor that serves to just absorb all the indices of this current. It's like a polarization spinor, let's say. And this product between these two spinors is defined by contracting the spinor indices with this symplectic matrix omega AB. It's defined this way. Great. So we can trivialize conservation by writing down our current in terms of this integral representation where we're just integrating over some twister. But then there is also an alternative representation of conserved current, which allows us to trivialize conservation in a different way with a different integral representation that looks now like this, where this auxiliary vector epsilon, instead of being contracted with this spinor set, is now contracted with a derivative with respect to this other spinor W. Where this spinor W now has an index downstairs, and we can interpret it as a dual twister now instead of a twister. Great, so we have these two different ways of trivializing conservation. One is via this integral over twisters, and another one is via this other integral over dual twisters. Right. So for now, we only main manifest conservation for a single current that is located at one point. But what we would like to do is to trivialize conservation for correlators that are located at multiple points. And let's just focus on the case of free-point functions of currents with spin S that each of these free currents are conserved. Then, if we want to make manifest that each of these free currents are conserved, we need to write down our free-point correlator in terms of free integrals over each of the free twisters that correspond to each of these currents. In this way, we would trivialize conservation for each of the free fields. Great. And we can choose to do this by considering that the free integrals are over twisters, or alternatively, we can also consider that the free integrals are over dual twisters. We can consider these two different ansatz, and both of them trivialize the conservation of each of the free fields. Great. So well, as we have just learned, this makes conservation manifest. And moreover, we can also make manifest the conformal symmetry of these correlators by considering that these integrands f and f tilde depend only on products between the twisters or the dual twisters, where they are contracted, the indices are contracted with this symplectic matrix omega AB. if we impose this form of this integrans f and f tilde, then the resulting embedding space correlator is going to automatically be invariant under conformal transformations. Hence, we made manifest both of these kinematic constraints, on our observable, both current conservation and conformal symmetry, by writing down our correlator in twistor space. So we can interpret these integrants f or f tilde as our correlator in twistor space. And we can also interpret this map, all these integrals as mapping our correlator in twistor space to our correlator in embedding space. Great, which we can then project and obtain the corresponding correlator in position space. Great, so also know that all these integrals are projective, and hence they are well defined as long as they are invariant under rescaling each of the free spinors. Hence, these correlators in twistor space must satisfy this scaling condition, which we can then use to bootstrap the corresponding bootstrap these objects via this scaling condition, because this f and f tilde must scale in a certain way, which allows us to obtain the following formulas for both f and f tilde. Here, these formulas are written in terms of an integral representation where we integrate over these so-called Schwinger parameters. The integrand on this representation can be easily seen to take either this formula for the first case and this other formula for the second case, for the case of dual twistors. Note that these correlators are, this correlator in terms of these so-called Schwinger parameters are super simple. It's just the product of n to the power of s or minus s. Right, so we just bootstrapped these correlators in twistor space or in terms of these Schwinger parameters. And we obtain these very simple looking formulas. And now we can just map them to correlators in embedding space to see what we get. And indeed, by performing the free integrals or the free twistors that I mentioned before, we can obtain the known 3-point correlators in embedding space of conserved curve. For example, for the first correlator, if we map it to embedding space, we end up obtaining the 3-point correlator that arises from higher derivative interactions in the bulk. Like, for example, f cubed for spin 1 or Riemann cubed for spin 2. And if we map the second correlator to embedding space, we obtain the correlator in embedding space that arises from leading interactions in the bulk, like Young-Mills for spin 1 or GR for spin 2. Note that these correlators in terms of the Schwinger parameters are remarkably simple, much simpler than the corresponding correlators in both embedding or momentum space. And also note that there is some double copy structure at 3 points, because if we square this object for spin equal to 1, which corresponds to Young-Mills, we obtain the same object for spin equal to 2, which corresponds to GR. So there is a simple squaring procedure where we can get the GR correlator from the Young-Mills correlator, which is something that does not happen at all in the embedding space or momentum space correlators, because their expressions are much harder. Finally, these correlators in twistor space can also be mapped to non-correlators in momentum space, and the details of this you can find this in our paper. But well, it's nice that we can also obtain the known results in both momentum and embedding space. Great. So to conclude, in this work, we found variables that trivialize all the kinematic constraints, which are these twistors. And moreover, we use them to expose a hidden simplicity of these 3-point functions of conserved currents. And the next steps to study what we can do with this formalism, it will be, well, first of all, to extend this formalism to higher point correlators, starting with 4-point correlators. Then it will be great if we can derive recursion relations that will allow us to deduce higher point correlators in twistor space in terms of lower point correlators. in a similar way as what happens for scattering amplitudes in flat space. And then we could potentially use these recursion relations to derive a possible cosmological Parker-Taylor formula, which would be an analogous formula than the one that I showed you at the beginning, that would give us like the endpoint correlator of gluons in Young-Mills in a certain helicity configuration to all n. And finally, now that we have a nice description of the kinematics of these correlators, we can perhaps use these twistors to interpret our correlators in terms of geometries in the space of kinematic data in a similar way as what happens for flat space amplitudes that are interpreted in terms of positive geometries. So that's it. So thank you very much.
Okay, so let's thank the speaker. Do we have questions? Okay, Joaquin, go on.
Hi, Facu. How are you doing?
Hi, Jorge.
Thanks for the nice talk. So if you could go quite at the beginning. The twistor space you're considering is a twistor space of embedding space.
Yes, you can interpret. I mean, yes, you can interpret like because then you can project these embedding space positions to the three-dimensional boundary. And you can interpret, at the end, you can interpret one twistor as a null line in Minkowski free. If you think now that the boundary spacetime is Minkowski free. So now one twistor would correspond to one null line. You can interpret it like that.
But if you want to think this twistor space you're talking about as a subset of some projective space, it would be a subset of CP watt or P watt.
I guess of CP3 because these guys have like 4 components and they are projective.
Oh yeah, the reason for my confusion was that you were using two 4-component spinors.
Yes, but exactly. But these 2 4-component spinors, they are somehow like a bi-twistor that would correspond to a given position in either the 3-dimensional space or a given light ray in the null cone. So let's say that a bi-twistor. So when you specify 2 spinors like λ1 and λ2, like for example here and here, you can basically form a line between them. And then when you specify 2 spinors, you have a line in twistor space that corresponds to a given point here in embedding space.
And that pi you have over there is a homogeneous coordinate in twistor space?
Yes.
Okay.
Well, I mean, it is a homogeneous. I mean, it parameterizes the possible linear combinations that you can have between these spinors, lambda. So it basically is a parameter that parameterizes this line he drew here.
Okay.
Okay.
Well, thanks.
We have another question by Arpan. Go on.
Thank you for the wonderful talk. So I had a question. So like you have talked about like bosonic correlators. So what about the fermionic correlators?
Well, actually, I mean, we obtained some formulas that we can of 3-point functions for all spins that we can, for example, evaluate at half odd spins, at fermionic spins, and we obtain correlators that match what you would expect from kinematics. You would obtain the known kinematic structures that correspond to fermionic correlators. So actually, you can obtain the known 3-point structures that correspond to fermions as well.
Okay, last question, Mati.
Yeah, Facu. So does this work for of the exceptional series for the tachyons in the zeta 4 also, or only for massless scalars?
So this this formalism, I mean, is especially works for massless and spinning fields.
Yeah.
But then if you consider scalars, well, okay, these massless and spinning fields in the Sitter-4, they are in the spinning exceptional series. But then if you consider scalars and you like take the formulas that we have and evaluate at s equal to 0, you obtain like correlators that correspond to the scale dimension being equal to 1, which is like the shadow of the conformally coupled scalar. So yeah, this is like what happens.
So it's only for the massless because you need to conformally couple, or maybe yeah, but I mean you get one mass, right? Because it's conformally coupled, right? Oh yeah, you don't get all the masses, all the spectrum of the tachyons.
No, you don't get. I mean, basically, in this formalism, you obtain stuff that satisfies this condition, delta equals to s plus 1. And if you naively evaluate s equal to 0, which is what we do for the case of scalars, you obtain scalar fields that have delta equals to 1.
Yeah.
Which are the shadow of the conformally coupled scalars.
Okay. Also, you mentioned that something about the conformal condition, right, or something. But for gravitons, you don't have that, or you do. You don't have the gravitons are not conformal in the Sitter-4.
Right. Okay. So when I was talking about the conformal symmetry, I was talking about the conformal symmetry in the three-dimensional. Let me see here. I was talking about the conformal symmetry in the three-dimensional boundary, which translates into the isometries of the four-dimensional bulk. So I was not talking. I was not saying that there is a conformal symmetry in the four-dimensional bulk.
Okay. Thank you.
Okay, so let's thank Facundo again for his very nice talk. And